In the direct method, the blade is designed starting from the distribution of blade angles at the leading edge and trailing edge, derived from 1D/mean-line design tools, or assumed by experience and past designs. The blade angle distribution and thickness is then specified along each meridional path line. The more Spanwise stations used, the more complex the blade shape can be. The problem with direct design is that it takes a lot of parameters to control blade shape with sufficient variety to have a broad design space. The blade shape is the input and blade performance is the output, so there is no causal link between the input parameters and the output. We only discover blade performance after analysis, and because blade angle distribution can be anything, then blade performance can be anything. So direct design encourages a trial and error design method, which is wasteful of time and resources. In the inverse design method, for both axial and radial turbomachinery, the work coefficient and blade loading is the input to the blade design. The blade geometry is calculated by the solver to satisfy the inputs and generate a unique 3D blade solution. This means directly controlling the aerodynamic performance of the blade and providing a more logical design approach. There are two key concepts that define and control the 3D inverse design method: the Spanwise distribution of work and the meridional distribution of blade loading. The definition of Spanwise distribution of work comes from the Euler turbomachinery equation, which links work to the rate of change of angular momentum of the working fluid, where RF and URF are reference length and speed, normally the outer radius and tip speed, and because power equals rotor speed times mass flow rate times RV theta, we can directly control the amount and distribution of work between the blade input and outlet by directly controlling the distribution of RV theta star. It can be shown that, for incompressible flows and for compressible flows, we can control the pressure or enthalpy difference across the blade by varying drV theta by dm. Note that the blade loading is always 0 at the trailing edge to satisfy the cutter condition. By controlling the Spanwise distribution of work and the meridional distribution of blade loading, we take total control over the blade performance. We are specifying not only the total amount of work done or absorbed by the blade and how much work at each Spanwise section, that is pressure ratio, or head, or pressure rise, or expansion ratio depending on the machine in question, but also where that work is done in a meridional sense, either in the forepart, aft part, mid-passage, or any combination of those within the same blade passage. A free vortex velocity distribution is generally used in centrifugal machines, but in axial turbomachinery, where the low peripheral velocities at the hub can create low momentum fluids and recirculation, we can directly reduce the work done in the hub region. We aim to maintain the same work overall, therefore we need to redistribute it to other areas of the blade. In this case, it is increased proportionally in the shroud region. From an aerodynamic perspective, this helps the flow at the hub, and it is typically recommended for axial rotor and stator configurations. But in rotor-only applications, particularly open axial propeller fans and pumps, this may lead to increased velocities at the shroud and high diffusion, and is also associated with high leakage losses. In this case, we have the possibility to use parabolic or spline-defined distributions which help to control the local distribution of RV theta. By reducing the shroud work, we help to dissipate the tip leakage losses, reducing the leakage flow and the impact on the following blade, which is what generates broadband noise. With inverse design, we have direct control over this aerodynamic design intent. Blade loading controls the distribution of work along the meridional path of each Spanwise section. No matter what the shape of the distribution, the total work, the area under the curve, stays the same, whether we have fore, aft, or mid-loaded distributions. The shape we specify becomes the pressure and velocity distribution for the blade. The blade loading is always 0 at the trailing edge to satisfy the cutter condition. The remaining step is to compute the 3D blade shape that will deliver this loading profile and overall performance. In the next video, we will look in detail at the inverse solver.